Baby, let me follow you down. All right. Song of the day, Baby, Let Me Follow You Down by Bob Dylan. All right, there's a great version by Bob Dylan and the band from the last waltz. Kudos to the band again. What are we doing today? Today we're talking about polynomials. We're talking about polynomials when we're given the zeros of our function. All right, we're going to review some polynomials and we're going to talk about it when we're given the zeros. I want you to find the function that it comes from. Okay. Tomorrow in our next video, we'll be given the function, find the zeros. All right. So here we go. Thoughts that come to mind here in polynomials. These are some thoughts that have come up in the past. Obviously, we're not able to do this part. Okay. But those are some things that come up to people in the past. Okay. Let's talk about polynomials in general. All right. Let's talk about the degree of a polynomial. A polynomial's degree, okay, is determined by the highest exponent. So it's determined by the highest, come on, highest exponent. All right, you're also going to hear this question, how many terms does a polynomial have? Well, the number of number of terms is determined by our degree. And I'll talk more about this minus 1. All right, I'll talk more about this in our next, in a couple slides here, but this is important as well, okay? Leading coefficient. Well, we know that a coefficient, like if I have the polynomial 3x squared plus 4x, the coefficient of x squared would be 3. The coefficient of x would be 4. The leading coefficient is the coefficient of the highest degree term. How do I want to say that? The term with the highest x coefficient of the term with the highest. All right, let me erase that for you. That's brutal. Degree. Holy buck. Wow, maybe I should start typing this out. All right, so now, here we go. End behavior. End behavior is some important stuff here, okay? So the end behavior of our function is determined by two things. Determined by our leading coefficient. I'm going to write that as LC. All right, and the degree. So our degree can either be even or odd. And our leading coefficient can either be positive or it can be negative. If I have an even degree function like this one here, and my leading coefficient is positive like this one here, okay, then my end behavior, so where my arrows are pointing when our function goes off to infinity, are both going to go up, up, and away. If my leading coefficient is negative, like let's say I put a -3, then they both go down. So when dealing with even degree functions, our end behavior are both going to go in the same direction. Now, and I'll explain more what this means later on, all right, but this is just a little chart for you. Okay? If I have a leading coefficient that is positive but my degree is odd, so if I had like 3x cubed plus 4, okay, then my end behavior would be down, up, if I was a positive, odd degree, so a 3, positive leading coefficient, so a positive 3, or if it was negative, it would go up, down, okay, and you're like, what is this chart? All right, well, this chart is our end behavior, okay, and we're going to come back to this, all right, and we're going to come back to this later on for sure, okay? So what are zeros of our functions? These are often also called roots. I'm sure you heard the term roots before. Okay, no, not the band. All right, so the zeros of our function occur I don't like using the word occur. What did I use last year? Only value. Okay, let's do that. Sorry about that. Scratch out occur for a second. Oh boy, what just happened? Hold on, something's going on. Alright, so sorry about that. It's the only value it's our x value. Y is equal to 0, or our function f of x, which is the terminology we've been using throughout this class, where f of x equals 0. The x-intercept, those are real zeros, non-imaginary. Why is this lagging so hard? Alright, real zeros. Okay? Pause for a second. Something's going on with my pen. I'm not sure what, but we're just going to have to battle here. Okay? But anyway, let's flip to the next part. Alright, so I have this polynomial x to the third minus 2x squared is x plus 2. Okay? So the degree of this polynomial, our highest exponent is 3. Our leading coefficient, well, there's nothing in front of that 3, or x cubed, so I can assume that it is a 1. Our end behavior, since it's an odd degree and a positive leading coefficient, so it's odd positive, that means it's going down up. Down up. Okay? Let's talk about, this is a little sneak peek of tomorrow, or our next lesson. Okay? So I want to talk about what happens, or how we would find our zeros here. This is a little sneak peek. Well, if I have 4 terms, remember 2 by 2 grouping. I remember doing this last year. I want to find the greatest common factor between these 2 terms. Well, the greatest common factor here is x squared. I'm left over with x minus, let's make the same color. All right, I'm left over with x minus 2 in the parentheses. Okay, my greatest common factor here, I want an x minus 2, but I have a negative x plus 2. All right, so I can take out a negative 1 and still have x minus 2. So I have x minus 2 twice, so I win that one. So this becomes x minus 2. And then I have x squared minus 1. Well, I know that this continues to factor. It's a difference of 2 perfect squares. All right. Well, so if I have x squared minus 1, 1 is a perfect square. That becomes, whoops. That becomes, oh, my phone is blowing up over here. All right. X plus 1, x minus 1. All right, so this whole polynomial here just became that. Our zeros, where if we set each factor equal to 0, so another little review from earlier this week. If I said this equals 0, get x equals 2, this one, x equals negative 1, and x equals 1. All right. That is fun. Let's keep going. Let's talk about the positive disco man. So disco man is y equals x cubed. All right, like it says here. All right, there are options here. I can have 3 real zeros. I can have 2 real zeros. Or I can have 1 real zero. Okay. 3 real zeros will look like this. That means my function will cross 3 different times. I'll have 3, 1, 2, 3 x-intercepts. Okay. This would be an example of a positive leading coefficient of an odd degree. All right. Our end behavior means our arrows is going down and up. If I have 2 real zeros, 1, 2. This could look something like that. All right. This could be a real zero. All right. This could be 2 real zeros, or it could be there's another option as well. This is called a double root here. If there's a bounce, whenever there's a bounce on our graph like that, that indicates a double root. So what would that look like? Like if I had something like this, where it was x equals -3 and x equals 2 and x equals 2. If x equals 2 appeared twice. That's what a double root is. All right. Lastly, I could have one real zero where my function only crosses once. That's a terrible disco, man. All right. And that's the other option. Okay. There also exists a quartic where y equals x to the fourth. All right. So I could have 4. 1, 2, 3, 4. I could have 3. 1, 2, 3. That's a double root right there. It's bouncing. I could have 2, so 2 double roots. Like that. All right. I could have 1. Or I could have 0. So all of these functions would be an example of an even degree function with a positive leading coefficient. Notice how they're both going up, up, and away here. All right. Ooh, I don't know if I'm going to fit all three of these slides in. Okay, so what this says about the number of roots. So what this okay, so what does it say about a number of roots? Okay, so meaning our degree. Okay, it being the degree of the polynomial is equal to the number of possible roots. Roots is a pizza place too, or zeros in the city. Great pizza, great pizza. What this says about complex roots? Well, complex roots, excuse me, or imaginary. Come in pairs. I want you to think about this. If I had x squared equals -4, and I took the square root of both sides, right? Oh my God, this is worse. Come on, buckets. Holy buckets. There we go. So if I take the square root of both sides, right? Remember, I can't take the square root of negative, but you cannot do that. You're right. But like, if I take the square root of -1, the square root of -1 is equal to I, right? So technically, x would equal 2I and -2I. So if I'm given that, if I'm given, hey, x is, one of your roots is 3I, then I automatically know that -3I is another root. Always. And I don't like to use the word always, but this always is going to be true. If 3I is a root or a 0, then -3I has to be a root or a 0. Same thing with irrational roots. Buddy, I call it the buddy system, people. They need a buddy. They can't go at this alone. What are irrational roots anyway? So if example of irrational root is root 2, okay, then -2 also has to be a root. Now, if you're in class, I do the same thing. You ready? If I give you root 4, well, that's a square root. That's a perfect root. So that's a perfect square. So that's a bad example. How about this? I'll make it go a little more complicated. If I gave you 2 root 3, then -2 root 3 would also be an answer. All right, if I gave you root 5, if I gave you negative root 5, then positive root 5 would also be a root. Okay? I'm going to stop this video here, and we're going to get to these two problems on our next video. All right, we're going to do these on the next video. I want to keep these together because they are very similar. All right, so pause here and pick up on the next one.